Hello, my name is Rafael Diniz. I'm going to present the paper with title Multi-Distance Point Cloud Quality Assessment. I'm the author of this paper. My name is Rafael Diniz, together with Mylene Farias and Pedro Garcia, all of us in University of Brasilia. So, this is a brief outline of what I'll present. I'll start with a brief introduction about point cloud quality assessment. Then I will explain a bit about our proposed method. Then the experimental setup, results and conclusion. So, what are point clouds? Point clouds are basically a structure that contains data related to 3D positions, typically X, Y, and Z, and color information, typically RGB, and sometimes other attributes like transparency, time of acquisition, reflectance to laser, normals, and so on. So, going to our topic. Concerning the quality assessment of point clouds, we can divide this quality assessment in two: subjective and objective quality assessment. Talking about subjective quality assessment, where humans give rates to the content, so it's based on humans perceived point cloud quality. We use in this article all the data that was published in 3 articles in the area, one by Cruz, Point Cloud Quality Evaluation Towards a Definition for Test Conditions. The other is Torligi, A Novel Methodology for Quality Assessment of Voxelized Point Clouds. And the last one by Alexiou et al., A Comprehensive Study of Ray Distortion Performance in MPEG Point Cloud Compression. With regards to objective quality assessment, objective quality assessment is the type that you use algorithms, you use software to predict the visual quality, right? A computer to predict the visual quality. So for point clouds there are some metrics especially based in point-to-point, point-to-plane, and plane-to-plane errors, and errors in both geometry and texture. So we use some metrics described in these articles. For example, point cloud quality assessment metric based on angular similarity. It's also called plane-to-plane. The other, a novel methodology for quality assessment of point clouds, which proposes the use of 2D image metrics for 3D point clouds projected in 2D planes. And the other, PCMSDM, that's a quality metric for 3D point clouds based in a mesh metric, a metric created for mesh content. So, going to our proposal, it's based in the local bind pattern descriptor, which is a well-established geometry metric. We also use geometry-based metrics for point cloud quality assessment based in point-to-point and point-to-plane errors. And our proposal is a multi-distance metric which uses 3 scores to have the final one. So our proposal is a full reference metric, as it uses the reference and the degraded point cloud to attribute a score. Right. So, how does LBP works for 2D images, right? In 2D images, LBP gets the neighborhood of a pixel. The neighborhood is well defined. As we can see here, we can just iterate in the neighborhoods, for example, from the right to left in a clockwise manner. And if the pixel has a lower value than the central pixel, then the target pixel, you get a label, for example 1. If the luminance of the pixel is less than the target pixel, you put 0, right? This is a basic form of LBP. And well, the characteristic of a 2D image is that you have a dense, equally distributed pixel in a 2D grid. And well, this is the basic LBP. As I mentioned, there are other LBP's variants like the rotation invariant LBP. So the steps of our proposed method I divided in 4 for this presentation. The first step is the voxelization methodology. The second one is the step that we create the feature map of the point cloud based on this adapted LBP that we developed. And then the third step, we compute the distance between the feature maps histograms related to the reference versus the test, reference compared to the test. And in the end, our final quality prediction model and how we get the final score for quality prediction. Right, our voxelization, basically we, before running any descriptor, we apply a voxelization that's important for the performance of the algorithm. The details of the voxelization is in this article we published beginning of the year towards a point cloud quality assessment model using local binary patterns. But basically we set the voxel size based on a size that provides a point cloud with a number of points around 60% of the original point cloud. Then we go to the point cloud LBP feature map extraction, where the LBP descriptor takes a neighborhood of n voxels. In our case, we get 8 neighborhood voxels. This is just abstraction. Is not exactly like this, right? Because the points are not equally distributed. The voxels, I mean, are not equally distributed in the space. But here we can have an idea of how the operator works. I just do more or less what is done in the 2D LBP, but visiting the voxels from the closer to farther away to set the labels, right? So after the feature map creation, we get the statistics of this feature map. That is the histogram of it. The frequency of each label gives frequency in the histogram, and then we make a distance between the reference generated histogram and the impaired point cloud generated histogram to calculate a distance between each pair of reference and impaired histograms. And then in the end, to get our final predicted score, we take a third degree polynomial function and put in this function D1, D2 that are point-to-point MSE metric that is provided by MPEG reference implementation, and the point-to-plane MSE that's also a metric provided by the MPEG reference implementation for point cloud quality assurance. And D3 is what I just explained prior. That is our distance. That's the distance of the point cloud, our adapted LBP for point clouds. We have this distance obtained from the histograms from the distance of histograms of the feature maps, and then we get the final results, putting all this distance in this third degree polynomial function, and through the least square method we get our final score. And this is our metric block diagram. You have the impaired point cloud, the pristine point cloud. In the top you can see our metric working with feature maps and histograms, and then in the bottom you can see the point-to-point distance, point-to-plane distance, going to the final regression model, to the final quality model that we use to get our final score. And then going to our experimental setup, we use this the data sets used, and also use the score of these three described by these three papers that I already mentioned by Torligi, Alexio and Cruz, that are here listed again. And we compared with these standard point cloud metrics plus the plane-to-plane plus some projective metrics, image projection based metrics, and we used three statistic tools: the Pearson correlation, the Spearman rank order correlation, and RMSE, to evaluate the performance of our metrics. And here with the ground truth described here in the left of the and the database also by three data sets. For the first one here, going top down, we were the best, and the second best was the point-to-point Hausdorff distance, and well, we were the only one higher than 0.9 in both PCC and SROCC, and also the lowest RMSE. And for the second database we were also the best by some margin, not so big but still. And for the third database we can say we were among the best in maybe a close second. The other ones that performed well or second best were the point-to-point MSE and the point-to-plane MSE, that also have for example, the PCC point-to-plane MSE has 0.003 better, and the SROCC it's 0.090, right, of difference. Not so much. We had the lowest RMSE still, so it proves our proposal is competitive, arguably the best compared to these metrics. So the conclusions are that we have evolved on our prior proposal, and so this our novel point cloud quality assessment metric works well, works even better when mixed with already established geometry based metrics, as we are a texture only metric. We only use the texture information, I mean. So this study seems to have promising results, and we already got some strong performance when compared to other metrics. So yeah, I think with this I finish my presentation. Thank you very much. Any questions you can address me through my email that's in the screen. Thank you very much. Bye bye.